All right, well, let's go ahead and start today's lecture. So last week we covered rapidly varied flow. We covered two cases of interest. So we first talked about hydraulic jumps, where we have a transition, a rapid transition between supercritical flow and subcritical flow. We talked about how we could compute the sequent depth and velocity downstream of a hydraulic jump, given the depth and velocity upstream of the hydraulic jump. And then we talked about weirs, which are a common hydraulic control structure that transition water from subcritical to supercritical flow. We showed how we could analyze weirs and come up with a weir discharge equation for broad-crested weirs. There'll be additional material in the type notes on sharp-crested weirs as well as non-ideal weirs, but don't expect that material to be on the exam. So today we are going to talk about our final topic of the class, which is gradually varied flow. So for those of you who have started on Lab 5, you've already got some exposure to gradually varied flow through the use of the HEC-GRASS software, which is the primary software used in industry for computing gradually varied flow profiles. Today, I'm going to introduce the theory behind gradually varied flow. I'm going to show how to derive the gradually varied flow equation that you can use to compute water surface profiles. And I'm going to go through examples of how you can essentially do what HEC-GRASS is doing yourself. So are there any questions before I get started? Nope, we're all good? All right, so let me quickly refresh your memory on gradually varied flow. So gradually varied flow, what was our definition of gradually varied flow that we talked about earlier in class when I characterized the different types of flow we'd be looking at? How about this? What was our definition for uniform flow? What was our definition for uniform flow? What was uniform about uniform flow? Yes? Constant velocity and yes, all three of those. So constant depth, discharge, and velocity throughout the length of the channel. So gradually varied flow is a more relaxed case in which the depth and velocity of flow are allowed to vary along the length of the channel. So for gradually varied flow, depth and velocity of flow, I'll say, vary along the length of the channel. But unlike the case of a hydraulic jump or a transition over a weir, the variance of the depth and velocity over the length of the channel is much more gradual. So in general, the slope of the water surface, dH by dx, will be much less than 1. So there are many different cases of gradually varied flow. I'll go over two illustrative cases here. So the first case I want to talk about is gradually varied flow in a steep channel. So this is similar to a homework problem that you are looking at. So let's say we have a steep channel. We have a reservoir that feeds the channel. Okay, and as the water comes over the top of this crest, it's going to transition through the critical depth. And then the flow is gradually going to transition into supercritical as we get it downstream. So note that as we move downstream, the depth of the water is decreasing. As I mentioned, the depth right at the mouth of the channel. This will be, the critical depth if it's moving from a reservoir into a steep channel. So this is the critical depth. This is some sort of reservoir. And this is a steep slope channel. So the flow in this channel would be supercritical. We're transitioning from the critical depth. And then that depth is decreasing as it transitions into supercritical flow. Note that here, the depth in the channel asymptotically approaches a constant value. So as we move further and further downstream on this steep slope channel, the depth is going to approach the normal depth. And for a supercritical, for a steep slope channel, which has supercritical flow, that normal depth is going to be supercritical. So this is supercritical in the channel. This is one case where you might find gradually varied flow. You will have some steep channel being fed by a reservoir or a steep channel being fed by a shallow slope channel. And as you go into that transition, the water will gradually transition from subcritical to critical to supercritical. And as you move downstream, it's going to approach its normal depth, i.e., you'll get uniform flow somewhere down here. And that uniform flow will be supercritical. So that's one example of gradually varied flow that's common to encounter. Let's go through another case. So here we might have a shallow slope channel. And let's say that shallow slope channel encounters an obstruction, for instance, maybe a dam. So at the upstream end, this channel, if it's a relatively constant bottom slope, this will be traveling at the normal depth. Again, this is the normal depth. But as we approach this impoundment, the depth of the water is going to increase, and you'll get something that looks like this. So here our channel, this is a shallow slope channel or a mild sloped channel. And our flow regime throughout this length is going to be subcritical. So this is often called a backwater or a backwater effect when you have some obstruction downstream that is causing water to back up. And again, the water will asymptotically approach the normal depth as you move upstream. Any questions on these two examples? Yes. The normal depth is the depth that occurs under uniform flow. So they could have called it uniform depth. I don't know why they call it normal depth, but it's the depth under uniform flow conditions. So for the first case, as you move downstream, you have a relatively constant slope over a long distance, and it will asymptotically approach that uniform flow depth. Same for the subcritical case, except moving in the upstream direction. Good question. Any other questions on these two examples? So our overall goal for gradually varied flow, for solving gradually varied flow problems, is given some information about the channel, so its geometry, its slope, and some boundary condition, so either the depth at the upstream end or the depth at the downstream end, our goal is to compute the entire water surface profile over the channel's length. So that would mean computing the depth and velocity at every point along the channel's length. So that is our overall goal. What I'm going to do next is I'm going to derive an equation that we can use to compute that water surface profile. This is essentially the same thing that is being done in HEC-RAS. I'll show you where it comes from in this next step. Are there any questions before I move on? Who's done lab 5 yet? Okay, a couple of you. Okay. So let's go ahead and take a look at gradually varied flow and how we can derive an equation for computing these water surface profiles. We're going to start off the same way we've started off every other equation we've derived in this class, which is we're going to start from the conservation of mass and the conservation of momentum. Sorry, not energy. So we have conservation of mass and conservation of momentum. So recall that our general form for conservation of mass, given in differential form, is dA by dt. So this is the change in volume or change in mass per unit time within our control volume, plus dq by dx. This is our mass flux through the control volume. The sum of these two terms is equal to 0. So again, this means the change in mass or volume per unit time within our control volume. dq by dx, this is our mass flux or volume flux through the control volume. For conservation of momentum, this expression is given by dq by dt plus dqu by dx. So this is our momentum, change in momentum terms, plus the elements of our force balance. So this will be g times a times dh by dx minus the bottom slope plus the friction slope is equal to 0. So again, this dq by dt term, this is the change in momentum. Well, it represents the change in momentum per unit time within our control volume. This dqu by dx, this represents the momentum flux through our control volume. And then we have these three terms which represent the different relevant forces acting on our control volume. So what did dH by dx represent? Which force? Hydrostatic. So it's analogous to the pressure force. This is the hydrostatic force. Which one is gravity? Bottom slopes. So this is the gravitational. And then the frictional slope, this represents the frictional force. So let's look at these equations in the context of gradually varied flow. We'll figure out which of these terms we can get rid of or simplify. So for gradually varied flow, we are generally talking about steady state gradually varied flow, unless otherwise specified. So we're talking about a water surface profile that is changing along the length of the channel, but is not changing in time. So for that reason, we can get rid of all of the unsteady terms. So we're looking at a steady state problem. So this dA by dt, this goes to 0. and this dq by dt, this goes to 0. So the next thing we can do, we can simplify this term a bit by applying the product rule. So this is something we did before when we derived the energy equation. But recall that from the product rule, we have d of qu by dx is equal to q du dx plus u dq dx. So I'm going to go ahead and take these two simplifications into account, and I'm going to move to the next page. So first, starting with conservation of mass, we have that dq by dx, the mass flux through the control volume, is equal to 0. So the mass in is equal to the mass out for any given control volume. So we have dq by dx is equal to 0. And then from the product rule applied to this momentum equation here, we can write our momentum equation as u times dq dx plus q times du dx plus g times a times quantity dh dx minus the bottom slope plus the friction slope is equal to 0. So just looking at these two equations together, are there anything that we can simplify here? There's something we can get rid of here. Yes. Right. So dq by dx is equal to 0. So if we substitute that in here, we get that this whole term here goes to 0. So the next thing I'm going to do is I'm going to multiply both sides by 1 over GA. And we can write out the rest of this expression just dividing through by the acceleration due to gravity times the cross-sectional area. So this here will become u over g. We'll get u over g times du dx plus dh dx minus the bottom slope plus the friction slope is equal to 0. And let's apply one more identity that we know. We know that the velocity is equal to the discharge divided by the cross-sectional area. So we have that du by dx is equal to d of q divided by a divided by dx. So we can apply another calculus rule. I'm going to apply the quotient rule. And just to give you a refresher, quotient rule says that if we take the derivative of the quotient of two functions, so d of f divided by g by dx. Note that this g here is just some function g, it's not the acceleration due to gravity. D of f divided by g is equal to df divided by, df by dx times the function g minus dg by dx times the function f, all divided by g squared. So this is an identity from calculus. You probably learned this in Calc 1. We can apply this identity to this derivative here. And we will get d of q divided by a by dx is equal to, okay, so let's apply the quotient rule. We have that our numerator is given by q, our denominator is given by a. So what'll this term here be? df by dx? dq by dx times what? A minus dA by dx times q, all divided by a squared. Can we simplify this expression? Which term can we simplify? dq by dx, what does this become? Why? Because of the first equation up there, right? Okay, just making sure you're all with me. So this is 0. And this whole expression becomes negative q divided by a squared times dA by dx. So we're getting close. I'm going to apply another calculus rule. I'm going to look at this dA by dx term, and I'm going to apply the chain rule. So dA by dx, this is equal to dA by dH times dH by dx. So this is the change in cross-sectional area with respect to the depth times the slope of the water surface. What is this term here? It's an identity that we talked about last week or 2 weeks ago. The change in the water surface, or the incremental change in the area of the cross-section with respect to the change in depth. What is that? Sorry? It's a geometric parameter. Which width? Top width. Very good. So the incremental change in the cross-sectional area with respect to the change in depth, dH, is equal to the top width, t. So this whole expression here becomes t, the top width, times dH dx. So taking that quotient rule plus the chain rule, what we end up with is du by dx, the change in velocity with respect to the length of the channel, is equal to negative q times t, the top width, divided by a squared times the slope of the water surface. So we can go back to the momentum equation. That says momentum. And let's plug in this expression for du by dx. So that's going to go in right here. And what we'll end up with is negative u over g times q, the discharge, times the top width, divided by a squared, times dH by dx, the slope of the water surface, plus dH by dx, the slope of the water surface, minus the bottom slope, plus the friction slope, is equal to 0. And now note that both of these terms here are functions of the slope of the water surface, so we can factor out that slope of the water surface. We'll get dH by dx times quantity negative u over g times q times t divided by a squared plus 1 minus the bottom slope plus the friction slope is equal to 0. And now note that we have discharge divided by area squared. So this is just going to become ut over a. This will become ut divided by a. Let's go ahead and write that out. I'm going to move to the next page. So we're going to take this expression. I'm just going to rewrite it. And I'm going to multiply these two quantities together. We will get dH by dx, the slope of the water surface, times quantity 1 minus u squared t divided by GA minus the bottom slope plus the friction slope is equal to 0. So note that for this expression here, I just switched the order of these and I multiplied these two terms together. So what is this term right here? Does that look familiar? Yeah, what is that? It's the Froude number squared. It's the Froude number squared. So let's just simplify that. We get dH by dx times quantity 1 minus the Froude number squared. So it's starting to look nice. Minus the bottom slope plus the friction slope is equal to 0. And now we can just rearrange this as a with the slope of the water surface as the dependent variable. And we get an explicit equation for the slope of the water surface. We have dH by dx is equal to the bottom slope minus the friction slope divided by 1 minus the Froude number squared. So this is our gradually varied flow equation. That can be used to construct the entire water surface profile, given some information about the channel geometry, as well as relevant boundary conditions, which we'll talk about in a little bit. So what kind of equation is this? In what kind of class would you encounter an equation like this, aside from hydraulics? It's a differential equation. What kind of differential equation? First order. Is it an ordinary differential equation or a partial differential equation? So this is an ordinary differential equation. All the derivatives are taken with respect to the same variable, dx in this case. And if the right-hand side were a linear function of the depth, then we could compute an analytical solution to this differential equation. Unfortunately, this is not a linear differential equation, so it's not something that we can solve by hand. Rather, it's something that we are going to need to simulate numerically. So for the rest of class today, I'm going to talk about how we can do that. Essentially, what we're going to do is we're going to do what Heckgrass does, but I'm going to show you how we can do it in Excel, how you can work through it and see how it works every step of the way. There's a few things we're going to have to do first before we get to your computers, though. First, we're going to have to define some of these terms here. And the second is we're going to have to come up with a scheme for solving or for simulating this differential equation. So the first thing we need to do is ensure that we can compute all of the terms in this differential equation. So the Froude number is just a function of the geometry and the discharge, essentially. But we need to come up with an expression for the friction slope. So what we can do is we can use the Chasey-Manning equation to come up with an expression for the friction slope. Recall that from Manning's equation for uniform flow, we have that the discharge is equal to phi divided by n as in November times the cross-sectional area times the hydraulic radius to the 2/3 power times the square root of the friction slope. For uniform flow, we had that the friction slope is equal to the bottom slope. For this case, it's not uniform flow, so we can't apply that same rule. If we rearrange this, we can get an expression for the friction slope. So square root of the friction slope will be equal to n times q divided by phi times the hydraulic radius to the 2/3 power times the cross-sectional area. And squaring both sides, we get that the friction slope should be equal to about n squared times q squared divided by phi squared times r to the 4/3 times a squared. So this is an expression we can use for that friction slope term. So this is the friction slope for gradually varied flow. So before we can go to simulate this, we need to come up with a scheme. As I mentioned, this is not a differential equation that we can solve by hand because it's nonlinear. So the SF and the Froude number will both be nonlinear functions of the depth. So it can't be solved analytically, but rather we have to come up with a numerical way of solving this equation. So let's try to come up with a scheme. I'm going to come up with a scheme for numerically solving the gradually varied flow equation. So numerically solving differential equations, is this something that you covered in computer methods? Did you cover forward Euler, backward Euler, explicit forward step, backward step? Does this sound familiar? Raise your hands if you've solved a differential equation numerically in computer methods. Okay, so I've got a few hands. It sounds like some of you didn't. So let's just go over the general idea of how one would solve a differential equation numerically. So let's say we have our diff EQ. We have dH by dx is equal to the bottom slope minus the friction slope, all divided by 1 minus the Froude number squared. So what we want to do is essentially approximate these infinitesimal quantities with discrete quantities. So let's just look at this dH by dx term. This is the slope of the water surface over some infinitesimal distance dx. So this is approximately equal to the following quotient. Let's say we break up our channel into little increments. I'll call each increment, I'll give it the index k. So we have hk plus 1, so that's the depth at some index k plus 1, minus hk divided by our spatial step size delta x. So this is basically just approximating that infinitesimal slope over some very small spatial increment. So we're taking this dH by dx and we're just approximating it as this quotient here. So this is approximately equal to bottom slope minus the friction slope over 1 minus the Froude number squared. So what we can do is we can rearrange this equation to give us the next depth at the next increment given the depth at the current increment. So let's take this expression and multiply both sides by delta x and then add hk to both sides and we'll get the following recurrence relation. Hk plus 1, that's the depth at the next increment, is equal or approximately equal to hk, the depth at the current increment, plus delta x times quantity S naught minus SF divided by 1 minus the Froude number squared. So the idea is we're going to start at some boundary point, either upstream or downstream, depending on which case we're talking about. And I'll talk about which point to use for which case. We'll start at some boundary point. From that, we'll have our depth at that boundary point. And then we compute the bottom slope, the friction slope, and the Froude number. From that, we can get the depth at the next point. And then we just start this recurrence over again. So note that the friction slope here, this is going to be a function of n, q, phi, and then the hydraulic radius to the 4/3 and the area squared. So both the hydraulic radius and the cross-sectional area are functions of what? They're functions of what quantity? H, right? So to compute those, we need to know the H at the previous not time step, but the previous spatial step. Similarly, the Froude number, this is given by q squared t divided by GA cubed. Both the cross-sectional area and the top width are potentially functions of the depth as well. So let me go ahead and draw out a schematic just to make this more concrete. Let's say we have a channel. I'm going to break it up into 10 increments here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say the distance between each of these increments is delta x. So what happens is we're going to start with some initial point. So let's say we start at the upstream end and we have some depth h naught. So this is our given boundary condition. This is some depth that we know. What we're going to do is we're going to apply this recurrence relation to compute the next depth in sequence. So in this case, we'll have h1 is equal to h naught plus delta x times this quantity here. So we'll have h1 is equal to h naught plus delta x times quantity bottom slope minus the friction slope from 0 to 1 divided by 1 minus the Froude number squared from 0 to 1. So let's just think about what these two expressions here are. We have the friction slope from 0 to 1. This is going to be equal to n squared times q squared divided by phi squared r to the 4/3. We'll leave a little space here, times a squared. Similarly, the Froude number squared from 0 to 1. This is going to be q squared times t divided by g times a cubed. So my question for you is, we have the hydraulic radius, the cross-sectional area, and the top width. Which value of h do we use to compute those hydraulic geometries? So it turns out that there are multiple choices for what to use. So we have h0, we're trying to get to h1. we're trying to compute the water surface profile along each of these points. So there are different choices one can make. This is something that may have been covered in numerical methods. The simplest way to do it is to just use the previous depth in sequence. Does anyone know what that method is called? So this is our first method for doing this. We're just going to use the previous point in sequence to compute the hydraulic radius, the cross-sectional area, the top width, and the cross-sectional area again. So there's a specific name for this technique. Does anyone remember what it's called? Yes? I guess in a way, because we are numerically integrating a function. I'm not familiar with that term being used for it, but it's possible. So there's different names for this. Probably the most common term you'll hear is either a forward Euler scheme or an explicit scheme. So let's just write out our scheme here. So this would be an explicit scheme. Sometimes called forward Euler. So in general, it'll be given by the following recurrence relation. We have that the depth at the next spatial step is approximately equal to the depth at the current spatial step plus delta x times quantity bottom slope minus the friction slope evaluated at the previous spatial step divided by 1 minus the Froude number squared evaluated at the previous spatial step. So this is probably the simplest scheme for solving a differential equation like this numerically. I should note that this is not just something that you'll encounter in hydraulics. This is all over the place in engineering. So whether you're working in structures or water treatment or energy or anything else, differential equations appear all over the place. So this is something that you will encounter at some point, no matter what your specialization is. This is probably the most common and easiest way of solving a nonlinear equation numerically. So let's go through how to do this. I'm going to go step by step for an example problem. There's one thing I need to note here before we get to the example though, which is what boundary point do you use? So it turns out it's going to be different depending on whether our flow is supercritical or subcritical. So be aware that for subcritical flow, we start downstream and step upstream. So you'll need a depth at the downstream boundary, and then you work your way back upstream. For supercritical flow, it's the other way around. You start upstream and you step downstream. So for instance, if we go all the way back to the two cases I showed at the beginning of class, for the subcritical flow example, we would need to know the depth at this impoundment and then work our way upstream. For the supercritical case, we would start at this critical depth at the upstream boundary and then work our way downstream. And this just comes as a consequence of how information travels for supercritical versus subcritical flow. For subcritical, disturbances can propagate upstream, So therefore, things that are downstream can affect the upstream water surface profiles. For supercritical flow, information cannot travel upstream. So we start with the most upstream condition and make our way downstream. Any questions on this concept? I know it's a lot today. So let's go through an example. This is going to be half tutorial and half in-class activity. So the full information for this problem can be found under quizzes, in-class gradually varied flow problem subcritical. And I'm going to start out this problem. So the full information is here. You're also going to want the following Excel file. So if you go under Files, Lecture 22, there'll be a Excel file called subcritical explicit method. So go ahead and download that file. I already have it downloaded here, so I'm going to use this one. But first, before I get to this Excel sheet, I'm just going to work on the problem on the board first. So our general goal is we want to compute the depth profile. We want to compute the depth profile for a backwater imposed by a dam and this is for a trapezoidal channel. So we have a channel that is terminating in a dam. The water surface might look something like this. We don't exactly know what it is yet. The depth of the water at the most downstream point is 2 meters. So we know the most downstream depth. The discharge is going to be equal to 12.5 cubic meters per second. So there's some water coming out of the other side of the dam, but we're not really worried about it. The bottom slope of the channel is 0.001. It's a trapezoidal channel. So the bottom width of the trapezoidal channel, B, is equal to 4 meters. The side slope, horizontal to vertical, is given as 1:1, horizontal vertical. And as I mentioned, the depth at the most downstream point is 2 meters. So the first thing I'm going to do is I'm going to go through and just come up with expressions for all of the different hydraulic geometries, the crude number squared, and the friction slope. So we're going to need those functions for when we go to compute each step of this water surface profile. So I'm going to go ahead and just write those down on the next page. So we have a trapezoidal channel. The cross-sectional area as a function of the depth is going to be H times B plus M times H. So H times quantity, B plus M times H. The wetted perimeter for a trapezoidal channel, this is going to be B plus 2 times H times the square root of 1 plus M as in mountain squared. The top width for a trapezoidal channel, this is going to be B plus 2 times M as in mountain times H. And the hydraulic radius, it's just going to be A divided by P. So I'll write this as AH divided by PH. Bless you. The friction slope, we can just write it as N squared times Q squared divided by phi squared R to the 4/3 A squared. And then the Froude number squared, this is Q squared times T divided by GA cubed. There's one other parameter that we're going to want to know. So in addition to the depth, we also probably want to know the water surface elevation. So I'm going to come up with an expression for the elevation of the bottom of the channel. So the elevation of the bottom of the channel, Z of X, as a function of the distance, is given by Z naught minus the bottom slope times X. So Z naught would be the most upstream point. So the bottom slope is Z minus, sorry, the bottom elevation is equal to Z at the upstream end minus the bottom slope times the distance. So we're going to need that for computing the water surface elevation. So with that, we should have everything we need. So what I'm going to do is I'm going to open up Excel and we're going to show how we can compute this full water surface profile. So just a few things before I get started. So all of our parameters are over here on the left. So we have all of our geometry parameters, the discharge, the depth at the downstream boundary. And also note that the way that I've set up the spatial coordinates, because we're going in the upstream direction, this is specified as negative. So 0 is the most downstream point, -10 is the next point upstream, and it goes all the way to 2,180 feet upstream. Sorry, not feet. This is probably meters. Yeah, 2,180 meters upstream. So the distance is specified as being negative in the upstream direction. And that's consistent with the equations that we derived earlier. All right, so first, we're going to start with this first row. So this will be all of these parameters at spatial coordinate 0. So we're going to compute the depth, the area, the perimeter, the radius, the top width, the friction slope, the Froude number squared, the bottom elevation, and the water surface elevation. So first, what can we put in here for the depth H? 2 meters, right? This is our downstream boundary condition. So we have a downstream boundary depth of 2 meters. So that's a given in the problem. The area, so this is given by our function for the area, which is H times the top width. So this is going to be absolute cell reference B6 plus M as in mountain. So that's absolute cell reference B2 times the depth H, that's E2. So I will paste that formula out below, but this just comes from the area formula that we specified earlier. Wetted perimeter. So this is given by the bottom width. So that's absolute cell reference B6 plus 2 times the depth E2 times the square root of 1 plus M as in mountain squared. So this will be B2 squared. So Don't forget these absolute cell references because, well, that's going to be important. Okay, so I ended up with a value of about 9.65. Okay, hydraulic radius, this one's easy. We just take F2 divided by G2, so the area divided by the wetter perimeter. This is F2 divided by G2. The top width, so this is B, so that's absolute cell reference B6 plus 2 times the side slope, so that's going to be absolute cell reference B2 times the depth, that's E2. Oops. I forgot to put an equal sign. All right, and I will paste that below. All right, the friction slope. So this one is kind of long. So this is going to be N, the Manning's roughness squared. So that's equal to absolute cell reference B5 squared times the discharge squared. So that's absolute cell reference B3 squared divided by H2 to the 4/3 power. So that's the hydraulic radius to the 4/3 power. Divided by the area squared. So that's cell F2 squared divided by phi squared. So that's absolute cell reference B10 squared. I don't think I have any parentheses, so I think that is correct there. Yeah, that looks right. For the Froude number squared, this is discharge squared. So that's B3 squared times the top width. So that's cell I2 divided by acceleration due to gravity. So that's absolute cell reference B9 divided by the cross-sectional area cubed. So that's cell F2 cubed. And I'll paste that below. Okay, finally, we have Z, the bottom elevation. So this is going to be negative D2. So that's negative D2, our spatial coordinate times B4, which is the bottom slope. So this is absolute cell reference B4. Oops. And water surface elevation. How can we get the water surface elevation? How can we compute the water surface elevation from the cells that we have? Two. In general, what would it be though? 2 plus Z. 2 plus Z. So this will be H, so that's cell E2, plus Z, that's cell L2. Okay, so that was a lot. Luckily, we don't have to do that for every row. This is what turns out. We can just pull these formulas down. There's one more thing we have to do though before we do that. We need to specify our depth at the next spatial step. So to do this, we go back to our equation that we derived for our explicit scheme. So we're going to have that the depth at the next point upstream is equal to the depth at the previous point plus the spatial step times bottom slope minus friction slope divided by 1 minus the fruit number squared. So we're going to apply this formula to our next value of the depth h. All right, so here we need the depth at the previous step. So that's going to be cell E2 plus our spatial step is going to be D3 minus D2. And then we're going to multiply by bottom slope minus the friction slope. So that's going to be absolute cell reference B4 minus the friction slope that we computed previously. So that's J2. All divided by 1 minus the fruit number squared that we computed previously. And note that we don't need to square this K2 because it's already squared in our formula. So this is depth at the previous step plus the spatial step, delta x, times bottom slope minus friction slope, divided by 1 minus the fruit number squared. And when I evaluate this formula, I get about 1.99. So the depth slightly decreased as we moved upstream. I'll paste this out, but I'm going to have to overwrite it pretty soon. Oh. Okay, so now what we can do is we have the depth at the next step. So what's the next thing we have to do? We have the depth at step 1. What's the next thing we have to do before we can proceed to the depth at step 2? Very good. So we have to compute APRT, friction slope, fruit number squared, etc. To do that, all we need to do, if we've set up our formulas correctly, is just drag this down 1 row. And it looks like it worked. So now that we have that, we can just drag this entire row down and our formula should work out. So I'm going to take all of the columns from E to M, as in mountain. I'm going to drag them down. And now I'm just going to double click this little icon here in the bottom right, and it should populate the rest of the cells. So you can see as we move upstream, that depth is decreasing. And we can follow it all the way down if we like. You'll see it starts to kind of tail off. So these are the computed depths. We also have the computed water surface elevation. So the water surface elevation is over here on the right. So one thing I want to bring to your attention before the in-class activity, there's a second sheet in this workbook that shows the water surface profile and the depth computed from the first sheet. I'll be around to help in a second. The second sheet, this has the water surface elevation here in blue over the channel bottom in brown. And the second plot here shows the water depth from the most downstream point on the right all the way to the most upstream point on the left. Did you have a question? For the roughness? Canvas had an extra 0. Well, Let's change it here and see what happens. 252. That seems like it's probably a typo, but we can try it. You should end up with something like this. All right, so is anyone having issues getting your Excel sheet set up or computing correctly? Yep. Z was but Z naught was 0, so yes. So go ahead and raise your hands if you're having issues, and I'll come around to help. You can spend the rest of class or whatever's left of it working on the in-class assignment. Otherwise, you are free to go, but I am going to come around and help those who are having issues. So go ahead and raise your hands if you're having issues, and I'll come help.